In this video, we're going to start using some calculus with our ideas of displacement, velocity, and acceleration, hence the calculus up here. So just to recap really quickly, we've got displacement, which is just where you are. So where you are, that's your displacement. And then we've got your velocity, which we said was equal to your change in displacement over time. And then we also have our acceleration, which is equal to your change in velocity divided by time. And we talked about using the idea of a road. Let's say this your displacement is 4 meters to the right, and let's say you're not stuck at 4 meters to the right, you're changing where you are, and you're moving at 4 meters per second. So in another second, you'll be at 8 meters to the right if your velocity is constant. But acceleration says, hey, your velocity doesn't have to be constant either. You can speed up, like when you're merging on the highway. You don't have to stay at 40. You can move all the way up to 70 or whatever you have to move up to. So that's displacement, velocity, and acceleration. Now, and I'll just write change in time here. Change in time meaning, like, let's say time starts at 0 and time ends at 3. Technically, it's not just 3, it's 3 minus 0. That's why I've got the little delta here. But so calculus says, let's take infinitesimally small changes. You might remember how before I said if your velocity, let's say I said your velocity, this is really your velocity average. Let's say your displacement is changing. And let's say you're also accelerating. Your velocity is changing every second. So if you say, okay, I started off at 0 meters, and I ended up at 4 meters, and so this is 1, 2, 3. So you're moving along the road, and that's out of the screen. You're moving along this road, and you say it took me 3 seconds, hence my velocity is 4, my final position, minus 0, divided by 3, and you say that's equal to my velocity. Well, actually, that's your velocity average, because if you were accelerating, your velocity in the beginning would have been less, and your velocity towards the end would have been more. You were speeding up as you moved along. Now, calculus says, let's get rid of these approximations, and let's tell you the exact velocity for every point you're at. And so calculus uses infinitesimally small pieces, and so we say dx over dt, a tiny change in displacement over a tiny change in time, and the acceleration would be equal to, the acceleration would be exactly equal to a tiny change in velocity over that tiny change in time. So, and you may recognize this right here is the derivative of x with respect to time. This is the derivative of velocity with velocity with respect to time. And so as we move down this column here from displacement to velocity to acceleration, all we're doing is we're taking the derivative with respect to time, and as we move up this column here from acceleration to velocity to displacement, we're taking the integral with respect to time. So what does that look like with some functions actually? This is a little abstract, and so let's do some functions. So let's say someone tells you, all right, we are moving with our displacement. If you want to know where we are, our displacement is governed by this function. So the sine of, let's say, 2t, and we'll add plus 3t plus 1. So they say, you give me a time, 1 second, 3 seconds, and you plug it into this function. So sine of 2 times 0 plus 3 times 0 plus 1, that would be equal to 1. That means at 0 seconds, I start at x equals 1. So I start right here. And like that, for all the different times, if you give me a time, I'll tell you where I am. You say, okay, that's nice. And you say, wait a minute, I can actually tell you your velocity if I take the derivative of this function with respect to time, so the derivative of sine of 2t. Now this is actually a bit of a review of the chain rule, but so the derivative of sine of 2t is the cosine of 2t, but we're not done, right? We got to take the derivative of that inside portion. The derivative with respect to t of that inside portion is 2, so let's multiply this by 2, and then plus the derivative of 3t is 3, the derivative of 1 is 0. So this now, this is kind of cool. This is a function that tells us the velocity at any instant t. So now we can say, all right, at time equals 0, plug that in here, 2 times the cosine of 0, that's 2, plus 3, you had a velocity of 5 meters per second, let's say forwards, at time equals 0. And we don't have to stop there, we can keep on going. Your acceleration is going to be the derivative of this function with respect to t, so the derivative of 2 cosine 2t, so the derivative of 2 cosine of something would be negative 2 sine of that something, which is 2t in our case. And then the derivative of the inside, again, is 2, so we need to make sure we multiply this by 2. That's just the chain rule. You have to take the derivative of the outside, and then you multiply that by the derivative of the inside. And then the derivative of 3 is equal to 0. So this right here, now you can say, all right, what was the acceleration at time equals 0? Well, the sine of 2 times 0 is 0. Negative 2 times 2, negative 4 times 0 is 0. You can say, all right, your acceleration was 0 at this instant. So as we move from displacement to velocity to acceleration, basically if any one of these was given, we could find the other two either by integrating to go up or by taking the derivative to go down. And all of this is with respect to t. Now, so we can also go in the reverse direction, which I think it'll be helpful to illustrate that with an example. So let's say you are given that the acceleration is equal to 3t squared plus 5. And right off the bat, what do you know? This acceleration is not constant, right? At time equals 0, acceleration is 5. Time equals 1, 3 times 1 plus 5 is 8. And so on. The acceleration is constantly changing. So all of our constant acceleration equations, like displacement equals time times velocity initial plus 1/2 a t squared, or velocity final equals velocity initial plus at, all those equations, those three equations that we spent some videos on, would not work for this at all, because acceleration is changing. So how do we go from acceleration to velocity? Well, we're moving up this arrow here, right? And so we're going to take the integral of this function with respect to t. So the integral of 3t squared, you may recall, is t cubed of 5 is 5 over 2. And this is just, we're doing the reverse of taking the derivative. And how can we check this? If we take the derivative of this, it should give us that. Now, we have to be really careful here, though. What would happen, and so I'm just going to write out plus c1, constant 1. You might think, why did I add this constant 1 in here? And you might be tempted to omit it, but that would be a big mistake. If we took when we took the derivative of 3, that disappeared. So when we integrate from here back, this is an indefinite integral. We don't know what constants we may have lost. Okay, so there might have been a c1 here that dropped out because the derivative of c1 is 0, and so we need to include this c1 here. How do we solve, or do we leave the c1 in indefinitely? Well, no. When we're given initial conditions, we can figure out what this c1 is and then substitute in 3, 5, or 17, or maybe it's 0 for that c1. At any rate, so let's integrate this to get the displacement as a function of time. So the integral of t cubed is t to the 4th over 4. The integral of 5 over 2t squared, this is a little ugly, but oh well. I believe that's 5 over 6 t cubed. Let's make that t a little nicer. Plus c1 times t. Do you see why it's so important that we keep c1 in? Plus a second constant, which again, this 13 would disappear, or 12 or 17 or whatever, would disappear as we go from here and take the derivative here. So we want to be careful that we don't, it could be 0, but it may not be. and so we don't want to have a wrong answer by omitting that. So this is the idea of calculus with displacement, velocity, and acceleration. All we're doing is we're taking infinitesimally small pieces so that we can get so that we're not stuck with averages, so we can find the actual velocity, acceleration, and all of these are functions of time.